All right, let's get started. So in the last class, we derived three equations. Particularly, these are not complicated, right? They just describe the linear relationship of your compression curve, your swelling curve, and if you like to combine both of these during unloading, reloading, and back onto the virgin compression line, then you can use the equation at the bottom of the slide. So in essence, if you recall, there are three equations. So this is for describing the settlement as you're traversing along the normal consolidation line. This is the equation if you're traversing on the swelling or the loading, unloading curve. And if you are traveling from the loading, unloading curve onto the NCL, then you would use something like this. And I hope that over the last couple of days you had time to just try to derive these linear equations by yourself. If not, it's actually quite straightforward. You'll probably do this in less than a few minutes. Anyhow, so let's use these equations. Often it's difficult to understand a concept until we do examples together. So let's extend our module a little bit more. So thus far we've looked at how to interpret odometer test data, how to get void ratio versus normal effective stress plots. We've also learned how to identify the pre-consolidation pressure graphically using Casagrande's method. So what we can do next is try to use our odometer test data that's plotted on void ratio versus normal effective stress to predict how much settlement we would expect. We can predict how much settlement we should get for, let's say, pure virgin compression, or for more complex scenarios where we are dealing with overly consolidated soils and moving back along the virgin compression line. So, if you look at this example here, again, you're given consolidation test data. As usual, you would see that in the first column you have pressure more or less being doubled per increment. You're given the void ratio, and there's essentially two sets of data here. So we start at 25 kPa, and then we go to 800 and 1600, and then we unload. So essentially what we're doing here is loading the soil and then unloading. And what you're essentially asked for is to calculate the compression indices. But instead they ask you to calculate the ratio of the swelling to compression index. Nevertheless, you have to calculate both to obtain that. The second part of the question asks if you have a E void ratio versus log normal effective stress plot, can we calculate the void ratio at a normal effective stress of 1000 kPa? So we can solve these two together. So first things first, let's take our tabulated data from our question and we plot it onto a void ratio versus effective stress plot. And you'll get a series of data points like this, and you do see that you have the loading phase and the unloading phase here. And beyond that, we have to calculate two things. We have to calculate CC, compression index, and then CS, swelling index. So to get our compression index, we want to borrow some data from, let's say, the loading phase of the problem. So it doesn't really matter which data points we pick. We can do this arbitrarily as well once we've plotted it. So we can just pick 2 points. We essentially want a slope, right? If you remember from the linear equations that we talked about, CS and CC are just slopes of a line, right? So to get a slope, we know we need 2 y coordinates and 2 x-axis, and the ratio of these gives us our slope. So you can arbitrarily pick these values for loading and from our loading branch, we can borrow the equations from the previous slide, but we won't need to do that because we're just calculating the slope. So we just look at a difference in y value between an incremental load. So you can more or less plug and play. 0.8 minus 0.7 over logarithmic of 400 over 200. Now, if you're still wondering where we got 0.8 and 0.7 from, once you plot, if you focus on the graph here, once you plot this curve, you might not get a very clean and straight line if you simply try to connect the dots. So there is a bit of fitting here if you take a look. Notice how this data point is not cleanly on the line. So what we can do is still try to force a straight line on our NCL line, because that's where the CC index is, right? And we can just extrapolate down. Let's say we have 200, and then we have 400, and you can go over here, and you can get 0.8, 0.7. So you're calculating the slope, nothing too sophisticated at this point. So we know our compression index is 0.33, and how about for the CS value? Well, for the CS value, we can use the same method, except we can probably go down to 400 and 200, but we have to try to pull up these void ratios here. So if we pull up these values, so we use 200 and 400 for the stress levels, and you would probably pull up some values like this in terms of void ratio. And you know that you can calculate the slope now to get your swelling index. So from the loading branch, you would get some value around 0.05. So you can't really stop there because the question asks for a ratio of compression indices, right? So specifically the question wants to know what's the ratio of CS over CC. And if you plug in these values of 0.05 over 0.33, then you'll get a ratio of about 0.15. So that's the first part of the question, part A. Calculate the compression index ratio. The second part of the question asks us to determine the void ratio at 1000 kPa. Well, this again is not challenging for us, right? Because we already know how to use these two equations. The question now is, where is the 1000 kPa? Does it fall on our compression or recompression curve? So I'll give you a bit of time to catch up. So, if we do the second part of the question, well, actually, we don't need these values again, but I'll plot them here. I don't know why they were deleted. 5.7 and 0.55, 200, 400, 200, 400. So, for the second part of the question, we know that void ratio of 0.8 at, let's say, sigma prime 1, 200 kPa. And we also know that we've calculated a compression index as 0.33. So the only challenging thing now is we want to calculate a new sigma prime. Let's call this sigma prime 3 now for simplicity. And we just want to know what's the void ratio when this is at 1000 kPa. So again, this is nothing challenging. You know this is just a slope equation. And we know our compression index is 0.33. We know the initial void ratio is 0.8. And let's call this void ratio 3 for this new void ratio we want to calculate. We have our ratio of stresses. And if we calculate E3 and solve for it, we'll get 0.8 minus 0.33. We'll get a void ratio of about 0.57. So yeah, so essentially sample 3 is just navigating along your two lines and knowing what the CS and CC values are. We can try to contextualize this into a plot of land. That's essentially what we're doing for ground improvement question, right? So we can repackage this in example 4 as some profile of land. So to do that, we can, well, I'll give you a bit of time. So to do that, let's look at another example. So in example 4, we're given a soil profile at the bottom left of the slide. And in this case, you don't have to calculate your compression indices, they're given to you. You have a sand layer here, and you have a clay layer. And on top of this sandwich of soil, you're applying a surcharge of 100 kPa on top. And for each of the soil layers, you're given your dry unit weight, you're given the saturated unit weight, you know the location of the groundwater table, which is just 2 meters below the depth of the surface of the land. You're given the saturated unit weight of the clay, and you're given some sort of void ratio to work with. Now, the question here asks you, how much settlement do you expect purely from primary consolidation? Now, this is a very good question for them to ask you during your interviews, right? It's quite common. I like to ask this at AECOM, I think, during the interviews. How much primary consolidation do you expect? So, in the first part of the question, you know that the clay is normally consolidated. The second part of the question, they ask you how much settlement is, if you know the pre-consolidation pressure, is 200 kPa, and the third part of the question is the same thing, but what if we reduce the pre-consolidation pressure to 150 kPa? And you're given the initial thickness of each layer here. The clay layer is 3.5 meters in thickness. So let's find the settlement for each of these three cases together. Now, part A, if we want to calculate the settlement of the clay layer here, there's one thing we need to do first. We need to know the effective stress. But how do we do that? Because the effective stress varies with depth. Well, for simple calculations like this, what we can do is calculate an average effective stress first. So we can take it at some midpoint in the clay for the effective stress to simplify things. So let's do that. So the average effective stress at the middle of the clay I trust we can calculate the effective stress, but here's the equation. We're not going to explain how. You want your effective unit rates. And since we're calculating at mid-depth, we just have 3.5 divided by 2, because we already discussed that we want the average at the middle of the clay layer. So if we plug all our known values in, our unit weight is 14. Minus 9.1. Half of 3.5 is 1.75. And again, we calculate our effective unit weights. And we get an average effective stress of about 76 kPa. So if you know your average effective stress, it becomes quite easy to calculate because you know what the surcharge was, right? The surcharge in the question was 100 kPa. So if we borrow and the question says normally consolidated, so you know exactly where you are on the virgin compression line. So if we borrow our expression derived from the previous slides, we know our compression index is 0.178. It's given in the question. We know the thickness of our clay layer was initially 3.5 meters, and you're also given your initial void ratio of 0.8 for the clay layer, if you recall in the question. So we know the initial effective stress was 76. We know we're applying a delta of 100 due to the surcharge at the surface. And we just assume that this delta is applied to the clay directly for simplicity. Then we would expect about just less than 13 centimeters of settlement for the clay layer for part A for this normally consolidated soil. The only thing to remember here is mainly that we normally take the average effective stress at the midpoint of the layer when we want to calculate things. All right, so next part of the question, we're given a pre-consolidation pressure. So before we do anything, we have to calculate where we are on the curve, our void ratio versus normal effective stress plot. So we know by now that the initial effective stress is 76. We know the surcharge is 100 kPa. So we know that we're at about 176 kPa and our pre-consolidation pressure was 200. So we know we're over consolidated, right? Because it's less than the pre-consolidation pressure. So because it's less than the pre-consolidation pressure, we know that we are on the swelling or the loading unloading curve. And we are given our swelling index in the original question. We know our initial clay layer thickness. We know the initial void ratio of the clay layer. And we know our initial and delta stresses. This is just about 25 millimeters. So this again, if you compare part A and part B, it can show you the power of surcharging. If you surcharge the cell before and you make it over consolidated, what happens is you get substantially less settlement, right? In part A, on the normal consolidation line, we're applying the same stress to both parts, right? Part A, we're applying 100 kPa. Part B, we're also applying 100 kPa. Now, the only difference is in part A, you're on the NCL line, so you got about 12 centimeters in settlement. But in this case here, on the rebound curve, you have a much stiffer soil. So you only get about 25 millimeters in settlement. Now, the third part of the question is more or less the same as part B, except you have a reduced pre-consolidation pressure of 150 kPa. And if you follow these two examples for part A and part B, you can probably guess what's going to happen for part C without doing any calculations, right? For reduced pre-consolidation pressure. So, part C tells us that, well, we have pre-consolidation pressure of 150, but let's just carry over some information. We know the initial effective stress was 76. So 76 plus 100 kPa surcharge is 176, and our pre-consolidation pressure is 150 kPa. So we have a criteria whereby our initial stress is less than our pre-consolidation pressure, and the pre-consolidation pressure is less than the initial effective stress plus our surcharge load. So based on this condition, we know that we have to traverse along the swing line and then back on the NCL line on the graph. And this would probably raise a red flag to you that we need to combine the calculation of the settlement for rebounding and virgin compression. Again, this expression is derived in 3 or 4 slides ago, so if you're not sure where this is from. Otherwise, it's a linear equation for 2 lines combined together. So we have all the information we need because the question provides everything, including both compression indices. 0.8. Consolidation pressure is 150 over 76. Plus compression index is given in the question is 0.178. Initial thickness of the clay layer is 3.5. Again, is 1 plus 0.8. Consolidation of 150. So the settlement would just be around 0. Or in terms of millimeters, 44.5 millimeters. So parts A, B, and C allow you to use each of the expressions for compression curve, swelling curve, and combination. If you were reloading beyond the swelling curve and back onto the virgin compression curve. So that's how you would use these three expressions. And you probably realize that if you try to visualize this graphically, this is nothing complicated. You probably don't even need to use these equations. If you can plot it out on a graph, you can just follow and extrapolate these values. So we can also do the same thing graphically. Let's say even if we give you the equations on an exam, you don't want to use the equations, you want to eyeball everything graphically, you can do the same thing. If you understand that calculating settlements from odometer data is nothing complicated, it's just graphical extrapolation. So we can do example 4 graphically. Hopefully the graphical approach will enable you to visualize what's happening from the odometer data, and it'll help you understand how we get these criteria and which equation or expression we should use. Now, so for the 5th example, we're redoing this question, but we're doing a graphical approach. Now, notwithstanding, we still need to calculate void ratios, right? So for each part of the question, we know that the void ratio is 0.8 initially. The void ratio at the end of consolidation calculated as follows. For part A of the question, we're just rearranging our formula to solve for void ratio. I'm not adding 170, I was going to say 176. I trust you know where this value is from by now. So we get void ratio there at the end of consolidation for part A. For part B and C, we do the same thing. I'll just write it out. Likewise, for part C, we need to find the void ratio at the end of consolidation. solve for void ratio. So these are the three final void ratios at the end of each part. Part A, Part B, and Part C from example 4. And remember, Part B's and C just have different pre-consolidation pressures of 200 and 150. And if you calculate these void ratios, what can you do with it? Well, you can plot these onto void ratio versus, or you're not done copying, here you go. You can plot these onto void ratio versus sigma prime plots. And then you can basically visualize what's going on along the stress paths. If you could not understand, for example, 4, why we had limiting conditions, why we're on the CC path, why we're on the CS path. So this is essentially working backwards. You can also try to plot everything out graphically. If you cannot visualize where you are on the stress path, you can try to do that. So these are parts A, B, and C on the graphs when you have the void ratios and you know the stress levels. So just please try to go through these on your own time and navigate on the void ratio versus sigma prime plot to make sure you understand how to use those three expressions to calculate settlement. We can make things a bit more challenging. Again, since we're doing reclamation and ground improvement, we can estimate settlements for typical geological profiles, as what you see at the bottom of the left here. We have a thick layer of clay on top of a competent rock stratum that we don't expect to move. You're given consolidation test data at the middle of the clay layer because, like we said, we like to calculate the effective stress at the middle. And you're given field consolidation curve interpolated from laboratory test in the right figure. So this question essentially asks us to calculate the settlement in the field caused by primary consolidation. So can we use lab data to estimate what would happen in the field? And we know that for this problem, we have a total stress applied of 60 kPa. The groundwater table is basically at the ground surface. You're given an initial void ratio of 1.1, saturated unit weight of 18 kilonewtons per meters cubed, and you have initial thickness of 8 meters. And from laboratory test data, if we look at this graph here, you have your void ratio versus the logarithmic effective stress plot, and you have an obvious change in stiffness of pre-consolidation at 70 kPa, and it's so linear, this plot, that you can extrapolate any CS and CC values that you would need to solve the question. So let's try to calculate the settlement caused by just purely primary consolidation. Now, we have to calculate the effective stress at the middle of the clay layer first, this 8 meter thick clay layer. So the initial effective stress is calculated as such. So the initial effective stress at the mid layer of the clay, we picked 4 meters instead of, because the total layer is 8, is about 32.6 kPa. You know your initial void ratio is 1.1. You know your surcharge is 60 kPa. So the initial stress level plus our surcharge is 32.6 plus 60 equal 92.6 kPa. So if we look at this value, 92.6 kPa, what does it correspond to? Well, you don't need to calculate anything because you can just extrapolate here, right? You can extrapolate this void ratio. So at 92.6, the void ratio corresponds to 1.045 from the graph. Therefore, we know the initial void ratio is 1.1, and we know that the new void ratio, due to applied loading of our surcharge load of 60 kPa, is the difference between the initial and that. So delta void ratio is about 0.055. And if you know your delta void ratio, then it becomes trivial to calculate. Your settlement. Initial thickness 8 meters, delta E is 0.055, initial void ratio is 1.1. So your settlement is expected to be about 0.21 meters, which is about 210 millimeters. So that's just another way to look at the question. So examples 3 to 6 are quite straightforward. If not, it may be a bit repetitive from what you learned from cell mechanics. Essentially, you want to know how to predict settlement using odometer test data. Moving forward, it's going to get more complex because we're not just looking at magnitude of settlement, we're looking at rates. I'm not just interested in how much settlement, I'm interested in when will we finish consolidation, when will we reach the settlement. So do work through examples 4 and 5, 3, 4, 5 again, and I'll give you an assignment soon, and I'll give you plenty of opportunity to practice using these equations to estimate the settlement value. Yeah, so that's essentially how we use our 3 expressions and odometer test data to predict settlement. Now, my iPad's really sensitive today. So we just finished talking about primary consolidation, but there's a latter part of the curve we haven't talked about. It's called a secondary consolidation. So this happens when primary consolidation is finished. And what's primary consolidation? Well, it's when all excess pore pressures that you generated from applying a surcharge to the soil have dissipated. So there's no more excess pore pressure. You're somehow at hydrostatic conditions again. And we mentioned earlier in the lecture that secondary consolidation is sometimes referred to as creep in soil. You have constant total stress, no change in pore pressure, but you still get compression, you still get settlement, and this is predominantly due to readjustments of the soil fabric. And from a consolidation point of view, we call this secondary consolidation. Now, since the definition is of secondary consolidation is that you're still getting compression at a constant stress level. So it doesn't make sense to plot our graphs in terms of void ratio versus stress level anymore, right? So if you look at this graph on the right of the slide here, to assess secondary consolidation creep, we often plot void ratio versus time. because this is a time-dependent problem now, right? So, how do we calculate secondary consolidation? So, after we finish reclaiming a plot of land, let's say the new Kowloon district, you might be asked a question from the client, how much further secondary consolidation creep do we expect? And you have to give a number. How do you estimate this number, right? You can't just pull this number out of a hat, right? So we do this by using odometer test data. We keep on leaving the odometer test there. We have a constant load and we keep on measuring the dial gauge to see if there's compression. And hopefully this process can be characterized using a single slope, right? It's hoping that it's quite linear. Of course, this is an idealization. So the secondary compression index, we talked about primary consolidation index, CC. There's a swelling compression index, CS, and there's also something called secondary compression index, which is also slope, idealized slope. And if you look at this expression, we're essentially trying to extrapolate a slope from a graph here. And we're interested in the slope of this curve here. So if you get odometer test data, let's say after primary consolidation is done and you keep on running the test for a couple weeks, a couple months, then you still have time and you have dial gauge readings which can give you void ratio, if you remember. And if you have this data, then you can deduce the second slope, because we talked about this is the initial compression, this is past your pre-consolidation pressure, and if you load and unload, you're here. But at some point, when all pore pressures have dissipated, you'll start getting a different slope here. And that's the slope we're interested in. So I guess it's easy enough to understand how we get C alpha, our secondary compression index. But how do we use this data to calculate secondary settlement? Well, it's actually done exactly the same way, right? You can just use a simple relationship of the slope, expected time frame. So let's say we want to know another 2 years after consolidation, what's the settlement, and you have this linear expression. We assume everything is linear. Now, of course, in reality, if you look at this graph here, it's never a clean-cut bilinear relationship, right? There's some curvature in it, and you'll probably have to fit two lines here to get some sort of inflection point as to when primary consolidation ends, and this line, for example, will enable you to get some sort of slope for secondary compression. So if you're interested about what the general order of magnitudes are for a secondary compression index, then for OCR clays, they're quite small. We're talking about 0.001. For NCL clays, it's a bit higher by maybe 3 to 5 times. Organic soils can be very high. Even after you finish consolidation, your organic soil can still exhibit a lot of creep, secondary consolidation. And if you want to characterize the secondary compression index for use here, it's defined here. And this is the void ratio at the end of primary consolidation. So that's how you would calculate creep. And we can use these equations together to do an example. So this last example that we'll do on pure magnitude, we will look at primary consolidation and creep to see how we can calculate both. So in this question, we have an NCL clay in the field. We're given thickness of the clay layer is about 2.6 meters. Your initial void ratio is 0.8. You're given the compression index of 0.28. You don't have to calculate your average effective stress this time. It's given to you as 127. You're applying a surcharge of about 46 kPa. You're given your secondary compression index here as 0.02. And the question asks, what is the total consolidation settlement of the clay 5 years after the completion of primary consolidation settlement? So since we're not looking at rates yet, this question has to give you some time frame for primary consolidation as 1.5 years, because we don't know how to calculate rates yet. We haven't reached that part in our lecture yet. So you're given enough information here to solve the problem. First of all, we have to take and calculate our secondary compression. And if you remember from just 2 slides ago, we can calculate secondary compression by using this expression. So EP is the void ratio at the end of primary consolidation. So we know EP must be our initial void ratio minus the change in void ratio at the end of primary consolidation. So the first thing we need to do is, well, how much void ratio change do we expect at the end of primary consolidation? And that's easy to do. We just use our CC curve. Right? So if we restructure this equation, then we can calculate delta E. And we know delta E is 0.038. So we can calculate the settlement solely due to primary consolidation. Initial thickness is 2.59, 1 plus 0.8. So we expect a primary consolidation settlement of about 0.054 meters. So the question asks us, what's the total consolidation settlement? So we need to know primary plus secondary. And we want to know 5 years after the completion of primary consolidation. So since we have a frame of reference for 5 years, and we're also given the secondary compression index, we can calculate that. So if we know that E naught is initially 0.8, we can calculate the void ratio at the end of primary consolidation as 0.762. So for secondary compression, we can calculate it just by replacing the compression index. This expression from a few slides ago, and we're given the secondary compression index as 0.011, plate thickness is 2.59, and we can use the time here in terms of years, because that's what the question gives us. So T2 is 5 years after primary consolidation plus 1.5 years for primary consolidation. Over the initial time is 1.5. That's why the question gave us time. So we can actually calculate secondary compression. So total consolidation settlement is equal to primary plus secondary. So we know that's 0.054 for primary, and our secondary is 0.0199. This gives us about 0.0739 meters. So the total settlement is about 79.9 millimeters, including primary and secondary. So then for practical projects, for example, for secondary consolidation, we calculate that, you know what, after 5 years, after primary consolidation, so it's 4.5 years, we will have additional settlement of 0.0199 meters. So that's just under 2 centimeters, right? So then if you're the client, then you can ask yourself, can I tolerate 2 centimeters of settlement after 4.5 years after? And well, if it's uniform, it may not be a big problem, right? It's only a big problem if you have differential settlement. So that's how you would consider both primary and secondary compression. So that's all you have to know for settlement for primary and secondary in terms of calculate magnitudes. The next part will get slightly more complicated as we look at rates. This is nothing new for you. I'm sure you calculated this during cell mechanics class. So in the next part of this module, we will look at how to calculate time. When will something finish consolidation? And of course, we'll go over the basic equations as well. So examples 3 to 7, please work through them again, and you'll encounter more of these pretty simple questions during your assignment. And let's summarize what we've learned so far in terms of odometer and consolidation. So the 3 most important equations are shown here. The main takeaways you should have are how to calculate the magnitude of settlement if you have a normally consolidated soil, and how to calculate the settlement if you have an over consolidated soil, how to calculate the settlement if you're traversing from the swelling line onto the virgin compression line. Obviously you would use this expression here. So all of these expressions are nice to get the magnitude, but they don't give us any information about the rate of settlements. For projects in Hong Kong, we are always concerned about rate. How long will it take before we can use the land? So in the next part, we'll look at how to calculate rates. And to calculate rates, we need to revisit Terzagh's consolidation theory, one-dimensional consolidation theory. What we can do now is, I think we can take a break first. We can come back in 10 minutes and we'll switch on to calculating rates of settlement for consolidation.
속도. 오늘 발걸리 있네.
彎晒啲牌，彎晒啲牌。點樣睇靚？係咪彎晒啲牌？係彎晒牌。嗱咁你係咪即刻彎晒？有啲喎，即刻彎咗真係。睇唔出嚟㗎，睇唔出啦。轉機嚟，中途轉機，唔係我變緊性㗎，純粹係化妝，我都啱啱先知。戴咗口罩就而家唔得添，係咯。我唔戴口罩都係唔得。翻唔到啊！
我都係要計數，計數。
輸俾男。
你呢再睇啦，第一次聽得明白，
真係輸俾男。係啊，真係
佢睇完嘅。係啊係啊係啊 ，yes。一買之後買就係咗，係咗。
好救命！真的是。佢隻聽得真百萬靚照仲未影機啊！有冇咁樣啊？如果借男人會依家冇晒人，宿舍好啊！呢個係之前咧，我哋問 power rap 嗰樣嘢，唔係我就 rap 係睇做咩？我都未 design。Keep 都係望多啲，學多啲啊嘛。我要 disability 3.5，disability 3.9啊！咩啊？但你係開 Facebook 成日都咁樣咯，跟住我寧願跳樓咯，跳樓咯，我跳樓，首先跳樓先。隔幾年即係話唔一齊同埋唔可以一齊爭三色燈同三色燈哇彎晒Jimmy 靚女啊！好似你睇咗好耐。你問我靚唔靚女？唔係問你驚喎。佢靚唔靚女？好靚仔。我都唔知話靚仔定靚女。係咯。好靚仔。泰文多謝。鴿仔。鴿仔電話，你冇帶？哦，好。啱。我想 check 下泰文鴿仔係乜嘢？係啊，你 search 下有冇查鴿仔？即係 Google Translate 喎。冇啦。點解？係喎，冇字㗎。我有。話俾佢話。新月話俾你。我咪跌咗。我美容。呢個5蚊嚟嘅。多謝。我留咗樓下。過食鹽隧道嗰邊。食鹽隧道真係5蚊咩？唔知有冇加價近排？有個名。有啊，食鹽隧道5蚊嘅。食鹽隧道係咪由荃灣去？有。荃灣大圍。荃灣飛去都得。咁遠咩？可以飛到？今晚係咩？唔知喎。咩料啊？個舞台食飯啊嘛。唔係啊，阿成。咦？都嚟埋。咁邊個唔飄喎？我唔知啊。係飄。冇同我講過。好多人嚟。地講過。 多人唔緊要啊，佢哋去啲熟食中心一定有嘅。咁你食唔食啊？你咪跟咯，你唔食咪跟埋隊咯。係啊，冇問題啊，冇問題啊。越多人開心，橫掂你全部都識我哋㗎，咪都係嗰班友。係啊。得啦，是但啦。OK，我哋尋日都食咗石河熟食中心。係啊。啊！你哋同佢開走啦。そうですね，都好優惠咯。係啊，你同佢約咗幾多次？即係你見過幾多次啊？已經好 firm 嘅。一齊打乒乓波，咁咩唔係啊嗰日？哦，そうですね。掛住嗰陣時候要開演唱嘅時候，你開演唱嘅時候就打麻雀，打波咯。係啊，而家唉，真係咪咯時間。我話價錢睇之前。
All right, let's carry on. So to look at rates, we will borrow Terzagh's 1D consolidation theory. Now, for this ground improvement class, I don't expect you to be able to derive his consolidation theory. But in the next couple of slides, I do want to explicitly show all the steps for the derivation, and in case you're interested in how we arrived at the formulation. What you do need to know is how to use the equations to calculate the degree of consolidation at a particular depth for different times. But there are some other things I do want you to understand, and this is the basic assumptions related to Terzagh's 1D consolidation theory. You should at least know what are the limitations of the theory. If you understand the limitation of the theory, then if you get discrepancies between field data and the values you calculate, at least you'll be able to explain the differences. So in the next 4 or 6 slides, I will show steps for derivation. I will only show them. You don't have to know how to derive the steps. But some of the things are interesting though, as we walk through the steps. You'll understand where we transition from calculating the degree of consolidation for a particular depth to calculating the degree of consolidation for an overall layer of soil. So after we explain some of the basics of where this formulation came from, then we can work on some examples together to calculate rate-related problems. So this is nothing new for you. From your soil mechanics class, we know Carl Terzaghi, the grandfather of soil mechanics, proposed 1D consolidation theory to predict how soil will compress with time. Now, there are of course some assumptions required for any theory. Any theory that we propose is only a mathematical representation of a natural phenomena. The theory is not meant to be perfect. And of course, you'll have some discrepancies, right, between theory and what happens in real life. So that's why often when we introduce new theory, we are always trying to outline the assumptions involved. Now, some of these assumptions may be quite apparent as we go through the steps, and some may not be that apparent. So the first one is we assume that we have a homogeneous soil layer, that it's not a heterogeneous soil layer. The properties are quite uniform spatially, is what we mean, with depth and laterally into the page. That's the first assumption, that we don't have any heterogeneity. The second assumption is the soil must be completely saturated. And you'll understand why in a bit, because the premise of this consolidation theory is that any volume change of our soil is mainly caused by reduction in voids. And if the voids are fully saturated, then any pore pressure dissipated will be equivalent to volume change, right? So that's quite important, assumption number 2. Assumption number 3 is, well, let's put it this way. The compressibility of the water phase, we assume it to be negligible compared to the soil skeleton. Okay, if you're thinking, is soil entirely incompressible? Well, no, but compared to soil, it has a very high bulk modulus. So we're talking about the difference between the bulk modulus of the two materials. So that's a fair assumption. I mean, if your water phase is compressing, you'll find it difficult to calculate volume change due to expulsion of water solely, right? So we have to make some assumptions. The third assumption involved is that our soil grains don't exhibit any localized granular mesoscale compression or any volume change at all. And this is in line with assumptions 2 and 3. The only volume change we're getting is from the dissipation of pore fluid and the rearrangement of the granular assembly. Now, as the title probably implies of this slide, 1D consolidation. So we assume that this is very much a scenario where the flow of water can only move in one direction, and that's vertically. We don't consider lateral dissipation of pore pressures, but when we look at the topic of PVD drains, prefabricated vertical drains, of course you have to consider horizontal dissipation of pressures, right? That's the purpose of installing drains in a layer plate to speed up the consolidation process. But for this part, we'll mainly look at just vertical dissipation of pore pressures. Last but not least, we have to assume that Darcy's law is valid, and Darcy's laws describe the flow of fluid in a granular material, right? You'll see later on in the derivation we have a very explicit step for Darcy's law. And so these are the 6 primary assumptions. Am I going to ask you to list them? Probably not, but am I going to ask you to derive this? No, but let's just go through this so we have a better appreciation of Terzaghi's 1D theory, and then when you do questions, you at least know what the limitations of the theory, right? So to come up with an expression to describe the time rate for consolidation, as per usual, we look at a very finite element of the problem. So let's describe the domain of our problem. If we just focus on this part first. Essentially what we're interested in is how this clay layer here will consolidate with time. And everything underneath the water table is of course saturated, and we apply some sort of total stress, and we assume that this total stress is entirely transmitted to the clay layer. And by applying this total stress, we do have some excess pore pressure generated, right? Because you can see that the groundwater table is initially here, right? And assuming that this is a hydrostatic groundwater table, by applying a load, we've generated some increase or some excess pore pressure. And this is the general expression for converting head to pressure, right? If we want pore pressure in units of kPa, we just times head in terms of length with the unit weight of water. So that's our excess pore pressure. And we have a clay layer with a thickness of 2 HDR, and we'll talk about why we look at 2 HDR, because we assume that there are 2 drainage paths. Since this is sand, this is sand, the drainage path is actually half of the clay layer. So we have 2 drainage layers here, so we call it 2 HDR. Now, if we look at the problem macroscopically, it's not going to help us derive anything. We have to look at the problem if we blow up this clay layer and look at it from an element perspective, then we can start looking at the conservation principles, conservation of flux inside, entering and leaving our element clay. Now, if we have a clay layer, let's, I think I can still draw. So we have dz, dy, and dx to describe this volumetric element of clay. And we have flux coming in. This is the pore fluid. You can imagine when we apply a surcharge to this element, the pore pressure won't dissipate upwards for this flow path, right? And if we talk about rates, we use partial derivatives. This is from your basic mathematics class, describing the change in velocity with this cubic element. So in much brevity, we can describe the movement of water through this finite clay layer by basically rate in, rate out minus rate in is your rate of volume change. We're interested in volume change when we're talking about consolidation problems. And we already mentioned that any volume change in a saturated soil is due to the expulsion of pore fluid from our soil elements. So if we want to describe the rates of water moving out of our elements, and volume change is described using uppercase V, so dV over dt, then we get some expression like this. And again, this is one-dimensional, so we're only looking at the change in velocity of our pore fluid in the vertical direction. So I guess this is easy enough to understand if you understand partial derivatives and rate problems, right? Now, we can, don't worry about this, you're not going to have to derive this, okay? But let's talk about this in terms of physical meaning. So we can, in the last slide here, we have an expression for the change in volume. And we can describe the change in volume over time using this expression in the red at the top. But we have to be able to characterize how the fluid is moving outside of our soil. So if you remember one of the basic assumptions I talked about, well, we said Darcy's law is valid. So Darcy's law describes the movement of fluid in soil in a granular or porous media. So if you don't understand anything, at least you recognize this, right? Darcy's law, V equals Ki. K is, of course, some permeability of the soil. I is the hydraulic gradient of the soil. And hydraulic gradient can be represented in terms of the difference in head over a certain distance, or it can be converted to pressure, as we talked about, head to pressure. So this expression here is basically Darcy's law, right? Written in partial derivative form. And we can, of course, equate these two expressions together, and you'll get something like this. So we're just combining our expressions to describe the volume change resulting from any expulsion of water. And the expulsion of water is described using Darcy's law. So the velocity of water leaving a porous media is related to the permeability of the media and the hydraulic gradient. So that's how we arrive here, this expression. Now, how do we further extend this to something we can use? Well, we kept on saying during the description of the assumptions that any volume change for a saturated soil must be from volume change of the voids. And that's why we care so much about saturating soils for element tests. We don't want there to be any air phase. Now, if we do that, then we can come up with an expression that describes any void ratio change is directly proportional to bulk volume change. And if you remember the relationship for void ratio, your void ratio is your volume of solids and voids, and that's the ratio. And then you can come up with the expression volume change dV over dt is equal to volume of solids, which is constant. Remember the other assumption when we derive this, the volume of the solids doesn't change, right? So it's a constant here. And the only volume change you're getting is the change in void ratio of time. So this is another expression. Bear with me for a bit. Now, if we want to further extend this problem, we have to come up with an expression to incorporate any volume change with void ratio. And if we substitute partial derivative of dvs with t and ds, then we can get this expression. And this, you might be wondering where this is from, right? This relationship? Well, this is from your mass volume relationships from basic solid mechanics. So if you flip back to your textbooks, you'll probably find this relationship. And we know that the volume is, well, 3 dimensions, dx, dy, dz. And then we can substitute the expression to get our change in volume with time. And it's a function of our void ratio. This is probably less important, but you can further manipulate the equations. So I strategically tried to use different colors to try to not get you confused. So this is purple. So if we combine these two expressions, then we can get a relationship of permeability, velocity of fluid, void ratio. Now, again, where are we trying to get with this? Well, we're trying to arrive at an expression to describe how effective stress changes, right? Because up to this point, we haven't talked about effective stress. We're only talking about the changing of volume, the movement of fluid outside of your soil. So let's try to move towards describing the soil behavior. So we know that any change in void ratio will have a linear effect on effective stress. Why? Well, because we know that the total stress is equal to effective stress plus pore pressure. And any expulsion of pore fluid must have some increase in effective stress. And we assume that it's a linear increase, okay? Is it really linear in reality? Well, it may not be linear, but I think it's a fair assumption that it's a linear change. Any change in pore pressure linearly increases with effective stress. And you can characterize that using this expression here. And the only thing we're not quite sure about, well, we can see change in effective stress, we can change in void ratio, but what's this A subscript B? Well, this is the coefficient of compressibility that we use to, you can use it to describe the stiffness of the soil, right? We want to know that how much does the void ratio change per unit of effective stress? Or how much effective stress do you gain per unit of void ratio change? So coefficient of compressibility can be viewed as some sort of stiffness parameter of the soil. Now, if we further combine this expression with what we derived earlier, we get another variable and we can isolate, we can turn this complex mass here into another coefficient. We call it the coefficient of volume compressibility, which is also describing the stiffness of the soil. And that's probably all you need to know for the focus of this class. And eventually, if you do further manipulation of the variables, you get this expression here. Essentially, you get something that you're starting to recognize, right? Coefficient of consolidation. What is that? Well, it's a very specific parameter that describes your permeability, the stiffness of the soil relative to the unit weight of water. We'll look at these variables later because I'll ask you to calculate the coefficient of consolidation. But for now, if you can't follow, that's fine. I want you to just recognize some of these equations because we will use them later on. So once we have that expression, what do we want to do? Well, coefficient of consolidation is quite important for us because it describes how a soil will consolidate for each type of soil. So we need to, we often only use this variation. This one is less common because we don't tend to refer to A subscript B a lot. So we have this expression now. And through this expression, from the previous slide, we have d over dv. We have a basic differential equation for consolidation theory. And to solve this equation, you know that in mathematics we need boundary conditions. It's not difficult to get, right? Boundary conditions. We know that at the interface between the consolidating soil layer and the drainage layer, that the pore pressure should be 0, right? And so these are the boundary conditions we adopt, and if we adopt some boundary conditions, we get some expression that can be used to describe pore pressure changes in soil. And we can further characterize with the time factor. And the time factor is something we use later on. It's just a dimensionless time. Does it really have physical meaning from 0 to 1? No, it doesn't. But we use it to graphically extrapolate data to calculate consolidation. So up to now, this is just a very brief introduction of Terzaghi's theorem. Will you understand it just by listening to me talk about these slides? Probably not. You'll probably have to derive it once on your own time. But I think it's better to show you all the steps, and then you can work on it on your own time rather than just to dump the equation onto the table. So if you understand none of that before, that's fine. But this you have to understand, right? Degree of consolidation. What is it? Well, it's your initial pore pressure minus the pore pressure at this time over the initial pore pressure. And if you know that this value is 0, then you haven't consolidated. If it's 1, it means you're finished consolidation. And you can, of course, further arrange to have 1 minus UV over U naught mathematically. And U subscript Z is just what your pore pressure is at a particular time. So if I told you the initial pore pressure is 100 kPa, and now the pore pressure at some depth is 50, right? Then you know it's your degree of consolidation is 0.5. What does that mean? It means you're halfway done with consolidation. That's all it means. So everything we derived so far will give you these expressions. You can calculate for the pore pressure at any specific depth you want for a soil layer. You have some time factor, and you have the degree of consolidation. Now, these three expressions are often used to come up with design charts for you to use in textbooks. I don't think you've ever had to derive 1D consolidation theory for any exam, even for soil mechanics. But this yellow box here will allow you to calculate the degree of consolidation at any depth in the soil. And that's basically all you have to know for my class. You don't really have to derive it, but it'd be nice if you understood where the expressions came from. So, what's wrong with this though? Well, are we really interested in the degree of consolidation at each depth? Not necessarily. When someone asks you, how much longer until we're finished consolidation? You're not going to say, well, at 4 meters, it'll take 1 hour. At 3 meters, it'll take 2.5 hours, right? No, you just want an average value. So, well, before we talk about that, yes, you can look at the depth of a soil layer, right? So here is some normalized depth Z over the entire drainage area, and you have typical drainage profiles, right? T V equals 0 means just start of consolidation, and if you have TV of some infinite value, then you reach the degree of consolidation, you finish the degree of consolidation, right? And at the boundaries, it's much easier to dissipate pore pressure and finish consolidation. And you remember during early on the slides, we talked about how at the boundaries near the sand layer, you have lower pore pressures. So this is a typical graph of if you needed to extrapolate at a particular depth, you can get the degree of consolidation. Now, as I said, we're not as interested in per depth, right? We can calculate it per depth, but we're usually only interested in the average degree of consolidation. So how do we deal with that? Well, you know that degree of consolidation is related to the settlement we have at this time over the total settlement from primary consolidation. If you do that, then we can plug in the settlement equation, and we can integrate over the depth of the drainage layer, and this will give us an average degree of consolidation. Because sometimes we're not interested in per depth. If you do this, then mathematically, eventually you'll arrive at some expression like this. And this is mainly what we use from day to day in our practice examples, in our calculation, and on your exam. And do you use this and try to calculate explicitly, and you try to put in different m values? No, we just refer to design charts. So what are these design charts? Well, we can actually describe the variation in average degree of consolidation using time factor and degree of consolidation. So you know that with some time factor towards infinity, that you'll reach a degree of consolidation of 1 or 100, right? So we can actually describe and fit these two expressions. It's not a continuous function, okay? So don't think it is. From about 0 to 60, we have to use this expression to fit the curve, and from anything above 60, so here, we have to use another expression. So this is basically approximation. It's not exact solution. So we often use, if you know that your degree of consolidation is just 30%, you would use this to calculate the time factor. If you know your degree of consolidation is, let's say, 80%, then you would use this expression. And you have various drainage conditions that we'll talk about later on. Now, where am I trying to get with this? Well, we actually don't need to extrapolate from a graph, because this is the table you often use when you calculate the degree of consolidation. You would just look at this column here. This goes all the way to 100, right? These columns. And your time factor would be infinity here, but based on your known degree of consolidation, you can extract some time factor. Right now it's quite abstract, but when we start doing questions together, you'll understand where all these graphs are coming from. So we often just use graphs to get the average degree of consolidation based on time factor relationships. Now, we'll come back to this in a bit. So based on that background, I guess the only way it would make sense is if we try to use these equations to apply it to problems, because just showing you equations and derivations is not going to help you, right? We have to try to apply it. So we can do a few calculations. The first one is, let's calculate the degree of consolidation at a particular depth explicitly. What do I mean by explicitly? Well, we can use iterations of different m values to calculate it, so you know exactly how painful it is and why we use design charts. And then we can just use a design chart. So let's do that. So we look at consolidation per depth, and then we look at average consolidation. But let's look at how we calculate consolidation per depth. Now, so these expressions would be given to you on an exam, right? So we have pore pressure at any depth. This is the expression. This is time factor, and this is degree of consolidation. So for this problem here, we already talked about this. We have some applied total stress to the soil. We have initial thickness of 2 HDR, and we have a clay sandwich between sand drainage layers. And this question asks us to determine the degree of consolidation at a particular height here. So at drainage layer divided by 3. And you're given a time factor here. So how do we use these expressions to solve this equation? So we're looking at this clay layer, right? So if you wanted to use this, solve this expression by doing iterations, you can actually do that, but we tend to not do that because it's quite onerous, right? And it takes a lot of time. So we know that at a drainage layer, a height of HDR over 3, and we know that m is pi over 2 over 2m plus 1. So we can do this and tabulate the data, right? So what we can do is we can do a tabulation of this data. Let's do this. So we know the height is 1/3, right? That's what the question asks for. We can do a few iterations. So the time factor is given to us in the question, it's 0.3. Small m here, small m is something that we use for iteration. So let's start off, in this question, let's start off with 0, do our first guess and check. So if small m is 0, if you look at this expression, what is this? Plus 1. Then you have large m is what? pi over 2, right? And if you take large M and you times it by the height, which is 1/3, then you get pi over 6. And 2 divided by M is about 1.273. If we take the sine of this, it's about 0.5. And if we calculate this, it's about 0.36. So where do these components come from? Well, we're trying to break this up so it's easier to calculate. So we've taken this here, and we're just trying to break up this difficult to calculate expression into tabular form. Now, the point of using this expression is to carry out iterations. So we have to repeat this process. So, but we know that the time factor is 0.3, and the next thing we do, this is an integer, right? So we got 1, perhaps. And you calculate all these variables again. Large M becomes 3 pi over 2. This becomes pi over 2. This becomes 0.4244. This is 1. This is 0.005. Now, what do we want to happen here? Well, we want this to equalize, right? To equalize to about 0. So we're not quite there yet, right? This is 0.005. So we can do another iteration. Time factor is this again, and the next integer is 2. So we know that large M would be 5 pi over 2, and then you have 5 pi over 6, 0.2546, 0.5, and you're pretty much there. You're at 0. And once you reach 0, the sum of this is across the horizontal scale is that, and you know that uz minus 1 is equal to 0.304. So this is about 0.6959. So this is about 69.5% of consolidation. So this is how we would do this purely from a computational point of view. But the issue is you normally wouldn't waste time doing this because you would just read it off a graph, right? So if you want to know what a particular degree of consolidation is for a particular mid-height for a particular time factor, what do you normally do from day to day? Well, you would just read it off a graph, right? If you know the time factor is 0.3, you would use this line. If you know that you want it at a height of here, then you would just go to this line and read off, and you would get 69.59% anyways. So there are different ways you can arrive at the same solution, and I hope you sort of understand why we don't really calculate this using integers and doing iterations, because it would be too costly in terms of time. So normally you would just get a graph and you read off the degree of consolidation. So that's what we would do for depth. Now, some other examples we can do are, what's the time required for a certain degree of consolidation? This is actually even easier, right? For example, if we want to know the time required for consolidating something 50%, and we know the thickness of the clay layer is 25 millimeters thick, we have double drainage, because this problem tells us we have drainage from the top and bottom, and we're given the time. In the lab, it should take about 3 minutes and 15 seconds. Now, the question asks us, in the field, how long will it take? Because in the lab, we only have a 25 millimeter thick specimen, but in the lab, if it's 3 meters thick, how long will it take? And we're doing this under the same applied pressure to reach 50% consolidation. Now to throw in a twist, the question says in the field if the clay layer is drained only at the top. So in the lab you have double drainage, but in the field you have single drainage. So just to refresh your memory on how to do these type of questions, well, we want to know at 50% consolidation what's going on. So we need to calculate the time factor at 50%. And we know the expression for time factor at T lab, drainage layer lab, should be equal to our field, right? We know that the time factor is constant. So if we rearrange the problem to make these equivalent, then we know that T lab over H drainage layer lab is equal to T field over H drainage layer field. So we know that in the lab it takes about 195 seconds because it's 3 minutes and 15 seconds to consolidate, and the specimen in the lab is 0.025 in units of meters, and in the field we don't know the time that it'll take because that's what we're trying to find out in this question. But we know that in the field we have 3 meters. Why don't we divide by 2 in the field? It's because in the field it's only single drainage, right? In the lab for odometer you have top and bottom drainage. You probably have a porous stone. So we take the field layer for single drainage as is. We don't divide it by 2. But in the lab we can take the thickness of our soil layer and divide it by 2 because the drainage path is half, right? Because you can have top and bottom in the lab. But in the field, you probably have some component layer and you can only dissipate this way. So we have to take the entire drainage layer. Whereas in the lab, we can take the drainage layer, divide it by 2. So if we solve for T field, then you'll get something around 130 days. So this is an example of how we take a specimen from the field, bring it to the lab, do an odometer test. And when we do the odometer test, we can use it to predict what will happen in field conditions. In this case, we assume that the time factor for lab and field cases are the same to reach 50% consolidation. And the only thing we had to change was the thickness of our layer here. So that's how we use our time factors. Now let's do another example together. So we're still referring to example 9. So that this part of the question asks us, how long would it take to reach 70% primary consolidation? Well, here's our expression for time factor first. So if we have this expression, and let's say you're given this table on the exam, so we want 70% consolidation. What we can do is, in example 9, we know that at U equals 50% in the previous question, the TV was 0.197. How do we know that? Well, if we go 50%, 0.197, and if we have U equals 70%, as in this question, TV is 0.403. So based on this knowledge, what can we do? Well, we know that T50 over T70 solve for T50 over T70. And you knew that this was 130 days. So we know T70 will about 260 days. So we can leverage the relationship between at T50 and T70. We know that the soil properties are the same, and we can calculate T70 as 266 days. Sorry, 266 days. So we can probably stop here today. I think we've done a lot of questions, so I'll give you a new assignment, but I want you to work through these assignments, not these example questions by yourself once, and try to derive Terzagh's expression by yourself once. And hopefully you'll get an assignment up this week, and you can do more practice problems, and we can finish off this module next week. Thanks for your time.